So section 7.5 in the book is a big overview, a review mostly of integration techniques, starting with the ones in Calc 1. So I'll go pretty quickly through this review of all the ways of anti-differentiating we know, starting with the reverse power rule, also known as raise and divide, and then some special antiderivatives for logs. You've got the antiderivative of 1 over x is the natural log of x, absolute value, instead of using the reverse power rule. That's a special case. And the antiderivative of e to the x is itself. Then if you have a different base, like 5 to the x, you have to also divide by natural log of 5. That rule does work for e also, since natural log of e is 1, you'd just be dividing by 1. And for trig, the main one to remember is that it reverses the usual derivative. So the integral of cosine, or the antiderivative of cosine, is sine. And you can basically reverse all of the trig derivatives. You write the chart backwards from the one that you have for derivatives. Cosine goes to sine, sine goes to negative cosine, secant squared goes to tangent, and so on. Then we have u substitution from Calc 1. There's a couple of u substitution problems there that you can do in your head. If it's just a multiple of x on the inside, then, for instance, integral antiderivative of e to the 2x is going to be itself e to the 2x, but you also have to multiply by a half because that'll cancel out the 2 when you take the derivative to check it. So these are u substitutions, but it's also, once you've done enough of them, you could just memorize that when you have one of those, you just have to divide by that multiplier. Same for cosine of 7x, you divide by the 7, or multiply by 1/7. Tangent and cotangent, those are u substitution problems, which you can also memorize the answer to. The way you do it with u substitution is to write tangent as sine divided by cosine, and then let u equal to cosine, and work it out from there. It turns out to give you the natural log of secant, since secant is 1 over cosine. For the inverse trig, it's basically a memorization process. The most common one is 1 over x squared plus a squared. When you take the antiderivative, you get the inverse tangent. The other one is 1 over the square root of a squared minus x squared, and that is the inverse sine, which you can take the derivative to check. Basically memorization as well. That's the derivative of inverse sine. And you notice that there's no need for the inverse cosine to show up as an antiderivative. The reason for that is actually because when you take that antiderivative of 1 over square root a squared minus x squared, the sine inverse and cosine inverse only differ by a constant. So you could make that one turn out, or by a sign there, so you could make it turn out to be inverse cosine as well. Just pull out the negative. And hyperbolic trig, just a couple that may come up occasionally. You can rewrite the hyperbolic trig as functions with e to the x in them and work these out, but then you can also memorize that the antiderivative of sinh is cosh, and the antiderivative of cosh is sinh. You don't need any minus signs when you have the hyperbolic trig. And then there's the new stuff. So here's the 3 trig substitutions that we have just recently covered, and this will be on the test. It has, whenever you see that square root, it might turn out to be on the top or the bottom of a fraction, then you can use these 3 substitutions. If it's a number minus x squared, you can use a sine theta, where a is seen squared inside the square root. If it's if they're added together, a tangent theta, and if it's changed around to x squared minus a squared, you can use a secant theta. And then the most recent ones, integration by parts. So you have antiderivative to do that's multiplied together, but the chain rule, reverse chain rule for u substitution isn't seeming to work. Then you can reverse the product rule, and that's integration by parts. There's the formula again. We'll just look back at the previous notes for examples. And then finally there's the newest one where you have big fractions. And for those, when you have a big fraction, you can break them up, you can do long division, and you can do partial fractions on them. And so next we'll do an example of that.